Okay, so thank you for coming along to one of the Bitesize Bioinformatics sessions. These are short little webinars where we go through one topic in bioinformatics and explore that. Today, we're going to be looking at loading in data into R. Okay, but we're looking at it with a particular idea, which is that in some cases, when you're loading your data into R, instead of just having a single data file that has everything that you need in it, your data may be split across multiple files, sometimes just a handful, but sometimes tens or hundreds of files. So we're going to look at an approach or a few approaches for how we can load these in efficiently without having to construct lots of code inside R. I will say at the outset, there are certainly multiple ways to do this in R. So whilst I'm going to show you one set of options for doing this, I'm sure there are other ways that you can do it as well. But hopefully in the examples that we've got today, we should be able to cover some of the main options that you have and a couple of the pitfalls that you might find when you come to do this. So I'm going to do this as a demonstration inside RStudio and work my way through a few different data sets. If there are questions as we're going through, people, please feel free to sort of unmute yourself and ask questions on the stream, or I've got the chat open as well, so you can stick stuff in there, and there will be plenty of time for any questions at the end if there are any. So let me share my RStudio session, and we'll take a look at what we're going to look at today. Okay, so what we're looking at here is a couple of different data sets. I've got an imaging data set and a set of genome data. If we take a look at the imaging data first in the folder down here, you can see that I've got a bunch of files, each of which is just a pretty conventional delimited text file. In this case, I've got some in a top level folder and some in a subfolder underneath that. And those are coming from different experiments. And then for my genome data, which I'll come on to a little later, we have the same idea. We have a lot of data files, but in this case, they're split by chromosome. So in each case, we have multiple data files that we need to load, and we want to aggregate them all together in R to be able to analyze them. So we're going to do the aggregation and the loading in the context of the tidyverse packages in R. So the first thing I'm going to do is just to load in tidyverse. Okay, so I'm going to look at that. And then I'll just load one of the files so you can see kind of what we're doing with this. So I'm going to start with the imaging data, and we're just going to use the standard read delim from the reader package in tidyverse to load this in. Okay, so I can select read delim. I can pick then the file that I want to load. So I'll go into imaging data, and I will just pick one of these files, and I will save that into a variable called data. Okay, you'll see that it loads in. And if I click over here, I can see what this data file looks like. Okay, so it's just a pretty standard data file, bunch of columns, different measures in each. And I have a whole collection of these files that I need to bring in. So the first challenge that I'm going to have is being able to specify the set of files that I want to load. And within R, we have a function called list files, which we can use to generate a vector of file names, which we can then use to load the data. So list files, to start with, will just take a path in which to look. So we can just say list files, and it would list the files in my current working directory. Now you can see that I'm not in the directory where my data is. My data is in this imaging data subfolder. So I can say list files in imaging data. List files with an S. And then it will make up the little vector of files and indeed folders that exist inside that location. Now, I don't want all of those. I want all the text files here, but I also have this OF folder, which is a subfolder of that. So I want to be a little more specific. So I don't want everything that's in there. I only want the text files from that. So my extension from this then is that I can do list files on my imaging data, and I can now specify a pattern to say what sort of text match do I need against the files in order for them to be kept in this search. And in this case, I'm not going to do anything fancy. You can build a full sort of regular expression, quite a flexible pattern for this. But here I'm just going to provide a text substring. So I'm going to say they've all got to have txt in their name. And that then will give me the text files that I want to load, but no longer the OF file. Now, I have one other thing that I'm going to need to take care of, which is that this is listing the file names here, but these file names came out of this imaging data subfolder. So if I try and pass those file names directly to a read function, it's going to fail because it's going to look in the wrong place for it. So the final option that I'm going to put on my list files here is going to be a thing that says full names equals true. And that means instead of just specifying the file name at the end of the search path, it actually puts the whole search path in, so that I'm going to get the path to that file from my current directory. So here it's going to be imaging data and then the file name. And that is something that I can specify and put straight into my loading function, my read_delim loading function. Okay. So having done that, I'm going to just spread this down the page so you can see it a little more clearly. So the three things: I'm specifying the folder in which to go and list the files, the pattern to specify which files in that folder I actually want, and then full names equals true to say that I want the full location of that file. And I will save that into a variable called imaging files. Okay, so I've got my little vector now of file paths. What I now want to do is to load all of those files rather than having to specify them individually. And the function I'm going to use to do that is a very useful generic function called the lapply function. Okay, so lapply takes two arguments. The first argument is a vector or a list. Okay, so in our case, it's going to be a vector. It's going to be the vector of imaging files. And then the second argument is a function. And what lapply will do is it will run that function and it will pass each of the items in the list into that function kind of sequentially. So in this case, we have a vector with 4 file names in it, and it's going to run the function we specify with the first file name in, then with the second, then with the third, then with the fourth. That will generate 4 lots of output, whatever it is that that function gives back. And that output then is going to go into a list, and the list will contain 4 slots, each of which will contain the output from the running the function. So in this case, the thing that I'm going to iterate over is going to be the imaging files. And the function that I'm going to run is the read_delim function from reader. Now, note, I'm specifying the function here. I'm not calling the function. So I put the function name, but I don't put brackets on the end. Okay. And that now is going to run read_delim with each of those sequentially. And if I save that into imaging data, if I run this, you'll see the loading running separately for the 4 different files. And I get back a list with 4 elements in it, okay? And the elements that I've got are going to be the loaded tibbles of output from the read_delim function on each of those. So I can say imaging data 1 will give me the tibble of data from the first file. Imaging data 4 would give me the tibble of data from the 4th file, okay? So now I've got all of the data loaded, but not really in the form that I want it. Okay, at the moment I have it as a list with 4 slots in it. So what I really want to do is to combine those and stick them all together into one big tibble with the concatenated data from all files. So the second component of this then is going to be a different function, which again is a generic function. It's not specific to loading data, but it's very useful in this context. And the function is called doCall. And it's a way of constructing arguments to functions in an automated way. What we're going to use is the bind rows function from dplyr, which is the way that you can join tables of data together. So bind rows takes in 2 or more tables of data that have the same structure, so kind of the same columns in the same order, and it will then essentially just stick them on top of each other to make one big concatenated table. Okay, so what we really want to have is a call that says something like bind rows, and then it would be imaging data 1, imaging data 2, etc., etc. Okay, but we've got 4 here, and that would be enough of a pain. But if we had like 40, that would be really horrible to type all of that out. So the do call function is going to take the hard work out of this for us. Okay, so do call takes 2 arguments. The first argument is the function that you're going to call. So in our case, it's going to be bind rows. And then the second argument is the list of arguments that are going to go into that function. So in this case, we can pass in our imaging data list, and it's going to put the 4 elements of that list as the next 4 arguments in the bind rows function. So it's just going to build that command line for us. The output of this will be the output of the bind rows call, which is just going to be one big tibble with everything in it. Okay, so I will call this imaging data combined. Take a second to do. And now what you can see is that the imaging data combined down here is one big tibble with all of the rows from all of the data in there. So you can see what each individual row has, what, about 1 million rows in it. So here I've got a tibble with 4 million rows, and I can see the combined results of all of those files. Okay, so everything is now combined into one file. So at the first pass, we've done what we set out to do. We've loaded data from multiple files, we've combined them together, and that's all good. However, we have a problem. So the structure of the file that we had was that it says X position, Y position, and then various other metrics that go off. And all of the files that we loaded have this same structure. So there will be a row in each of those files that says X equals 0, Y equals 0. So I've got 4 rows that look like that. And I've got no way in the current data structure of being able to tell which file they came from. So we need to have that. Otherwise, yeah, in this structure of data, we can't tell where each one came from. So if you had data where you simply can load it and stick it on top of each other and that's enough, what you see here would do the job. But we need something a little more complex because we need to know which data file each of our rows in our final tibble actually came from. So how are we going to do that? What we're going to do is we are going to build our own little mini import function. So rather than just calling read_delim, we're going to write a function to do our file import. And as soon as we have our own function, we can then customize that to do more clever things with it. Now, that brings us on to how to write a function. And the way that I'm going to do it is the way that I often do when I'm building these functions. So you can build functions, but they're quite difficult to write in the first instance because you write the block of code, but you can't run it sort of individually. You can run the whole function, but you can't sort of run each individual statement. So it makes it a little more tricky to develop. So a trick that I use quite commonly when I'm doing this is that here what I'm going to build is a function called readFile, and it's going to take a single file argument. So what I'm going to do is to make a variable called file, and I'm going to populate that with the first file name from my list. Okay, so here it's going to be imaging files 1. Okay, so I have a variable called file. I can now write some code and pretend that file was an argument to a function. Okay, so I can use file in the way that I would use it inside a function call. So I can say read_delim file. okay, which will read that in and give me my tibble of data. What I then want to do is that I want to add a new column to this that says the file name that came from there. So I can pipe out of this into the add column function. And I'm going to say what my column that I'm going to add is going to be called. So I'm going to have a column called file name, and the contents of that column are just going to be the file name. So I say file name equals file. So what that will do is to create a new column called file name, which I can't see on here. Let me make this a little wider. Okay, so I've made a new column called file name, and in that is the file name, and it's been tagged on every row inside here. Okay, so that now does what I needed my function to do. So I can take this code and turn it into a function. So if I say this, so I'm putting a function definition where I'm making a function called read file. My function argument is the same name as the temporary variable I set up. I can now put this code inside the function, and it's all ready to go. I can get rid of the temporary variable I made before. So I can say rm file. Doesn't really matter if I do that or not, but it just cleans up my environment a bit. And now I can execute this function definition, and I now have a function called read file, which is basically just read delim, except that it now adds a new column to put the file name in. The final modification I'm going to do on here is that the output of this add column is what I want to send back. So I'm going to pipe that to a return statement so that it then sends data back from the function to the person that called it. Okay. So it now means that I can do read file from, say, imaging data and the first one. And what I will get back is the output of the function with the file name on. I can now replicate exactly what it was that I did before. So all of the stuff I did here, where I did my lapply and my do call, except that now, instead of running the read delim function, I call the one that I've just created, read file. So now I can say lapply imaging data, imaging files, read file. That goes into imaging data, which is going to be my list of 4 elements. And then I can combine those using the same do call function as before. And now if I look in my imaging data combined, I'll see that I have all of the data in here, but I now have the file name on the end of this. So if I sort by X and Y, let me do that. There we go. So I can see now that I have 0, 0, 0, 0, 0, 0, 0, 0, but I can see that these are from now different files, ROI1, 2, see ROI1 and ROI2. So now I've got a combined data set where I've got all of the data and I can tell where it came from. A couple of other extensions from this. So at the moment, I've done list files and then specified the folder that I've got. But my data actually inside imaging data has a bunch of data files in here, but actually there are more data files inside this subfolder. Okay, and often, again, you might have a whole tree of folders that contain files you want to load at many different levels inside there. So one other little extension I can do to the initial generation of the list of files. So originally up here, I had my list files code. Okay, we put on the pattern and the full names equals true. An additional option which can be useful is recursive equals true, which means that it's not just going to look in the folder that you specify, but all subfolders of that as well. So if I run that, at the moment, I've got 4 imaging files from running this. If I run it with the recursive on, you now see I get 8 imaging files. And if I have a quick look at those, you'll see that it's picked up the ones in the imaging data folder and in the OF subfolder of that. Okay, so if you need to do the search further down, that would then allow you to do that. And then loading those is exactly the same as before. It's the simple lapply and do call on top. Okay, so that solves most of the problems we have. Let's have a look at another data set, because the other data set is going to be largely similar, but with some other tweaks that we're going to need to look at. This time we're going to look at the genome data folder. Okay, so here we have data from a whole load of chromosomes in here. So I'm going to do my same list files. I'm going to list in genome data. And I'm going to say full names equals true and see what I get. Okay, so I can see that I get all of the data that I want, but I have this README file as well, which I don't want. Okay, I want all the chromosome data. And unfortunately, I can't do the nice little trick I did before and just say pattern equals txt, because README is a text file as well. I could try and find something else to specify, so I could say pattern equals CHR. That would work in this case, but let's take the opportunity to just show an option for specifying a slightly more complex pattern. So in this case, if I wanted to specify both that I needed CHR and TXT in it, the way that I would do that would be to build an actual pattern. So the pattern that I'm going to build is going to be, it's going to have CHR. Then I put in the sort of flexible part of this. So in a pattern, a dot here means anything. Okay, so you can have any character at that point. You can then add after the dot a star, and the star means any number of anything. Okay, so what it's going to look for somewhere in the file name is CHR with a capital C, then anything you like in the middle, and then TXT on the end, which will now find me only files which have CHR something, and then TXT on the end. Okay, so that gets me the chromosome files, but it doesn't get me the README. Right, that's going to go into genome files. Okay. Oops. So let's run that. And again, I can load one of these. So let's load the first of these genome files, just so we can see what's in there. Let's see at the top on here. Okay, now it's quite a big file. So what I'm actually going to do is to pipe this to the view function so I can see it in the little graphical viewer. And in this instance, I can concatenate all of these files together because the only difference between the different files is the chromosome, and the chromosome is already a column in here. But what I'm going to do is actually do a little bit more preparation on this data. So there's some changes that I want to make. So here I've got a column which is called probe, but actually what it's really got in it are gene names. So I want to change that probe to be gene. I've also got some fields that I don't really want. Also on names, I'm going to change probe for gene. I'm also going to change this thing that says probe strand just down to strand, because again, it's the strand. And then I've got feature, which is the same as probe. I've got ID and a description, feature, strand, type, feature orientation, and distance. And there's a whole load of columns there that I don't want. Now, one of the things you find when you're loading big data sets is that if they have a lot of extraneous information that you don't need, then loading all of that data initially and then filtering it afterwards can be quite memory inefficient. So if you had a large amount of data in each of these files that you knew you didn't want, then rather than loading it all in initially and then filtering, it's a lot more efficient to throw that data away at the point where you load each individual file so that it never occupies the memory of kind of all of the data. So we're going to again build a custom function, but we're going to do a little bit more cleaning and filtering in that function to try and get us the minimal amount of data and to optimize our memory usage when we load the data files. So as before, I'm going to use the same trick as before. I'm going to make a little temporary variable, which is going to be the first file out of my genome files. And then I'm going to build the code that's going to read this data. Okay, so it's initially just going to be a read delim of the file. I want to sort out two of the column names. So I want the probe column to be called gene. So I'm going to use the rename function and say that gene is going to be equal to probe. That means I'm making a column called gene out of what was the probe column. Okay, so now that's called gene. I'm also going to turn probe strand into strand. It will be another rename operation. So I'm going to make a column called strand, and that's going to be probe strand. Because probe strand has space in it, I need to quote it. And you can see up here that when you're quoting column names, you can't use single quotes or double quotes. You have to use these little backticks. So let's do that. So that's now fixed the gene column and the strand column. And then I want to get rid of all of the columns between the feature column and the distance column, which was down here. So I'm going to get rid of feature, ID, description, feature strand, type, feature orientation, and distance. Okay, so everything from there. So that's going to be a standard dplyr select. And the quickest way to do this is with a negative selection. So I'm going to do a negative range selection. Okay, so a range selection is you specify the first column, colon, and the last column. Okay, so in this case, it would be from feature, colon, through to distance. Okay, so if I did that, that would select the columns between feature and distance, like this, which is the exact opposite of what I want. I want to get rid of those. So I need to do a negative selection. So I put a minus in front, and then I need to put it in brackets so that it knows that it's kind of the negative of all of that range. So select the columns between feature and distance, and then the minus in front means remove them rather than keep them. So then I get to the data I actually want, which is just the gene name, the chromosome start, end strand, and the data from this. Now that that's built and I can see that it works on one file, I can turn it into a function. So I'll call that read genome file. It's going to be a function. And again, I will use file as the argument name. I put all of this code into the function, and I add a return statement to the end so that the output of all of that gets sent back. I can clean up my environment by removing the temporary file variable, and I can execute this function so that I now have a read genome file function. Okay. Now we're into the same process as before. So I'm going to use my lapply. So I'm going to do lapply across my genome files, and I'm going to use my read genome file function. And that will go into the genome data, which will be a list. Okay, so it's going to go through all of the chromosomes. It's a bit more data this time. There's what, 21 data sets in this. Okay, but again, same problem sorted. We now have a list of 21 elements. Incidentally, when I'm combining these, for kind of clarity in this session, I'm putting them into a different variable. But if I was doing it for myself, I wouldn't keep both the list version and the combined tibble together. I'd just overwrite. So now we want to do the do call. So we'll do the do call bind rows, and we're going to do that off the genome data. And when we do that, we're going to get an error. So there is an additional problem that we might come across here. So when you load your data files, one of the things that Reader does is that it looks at the contents of your files and it uses the content of the file to decide what data type each of your columns is going to be. Is it going to be a numeric column, or is it going to be a text column, or date column, or a logical column, or whatever? Okay. And the problem that we have here is that we're trying to combine two data sets, and the guess that it has made for one of those columns is different in those two data sets. So it's saying it can't combine the chromosome column from the first data set with the chromosome column from the 20th data set. Let's go and have a look why. So if I look at genome data 1, okay, my chromosome column says that it thinks it's a DBL. DBL is a double, which is a numeric data type. It's double precision floating point number. And it thinks it's a number because the chromosome values are all 1. If I look at the 20th item in the list, you can see this one is a character column, it's text column, and that's because we're on the X chromosome. So because we loaded all of these files independently, it's made different guesses for each of them, and now it can't combine them because it goes, well, that chromosome column, it's a numeric column in some of them, and it's a text column in others, so it won't put them together. So we need to fix that. We can fix that by going back to our read function, and all we're going to do is we're going to force the data type for that column. Okay, so whatever it thinks it's going to auto-detect, we're going to tell it we know better. We know that a chromosome column needs to be a character column, a text column, even if it only seems to contain numbers in this data file. So the option that we're going to use for that then is that we're going to set the col types argument. Okay, col types allows us to force column types. We only need to force it for the ones that we want to override. All the rest will still be auto-guessed. And the value for that needs to be a call to the cols function. And the cols function, you name the column that you want to force. So in this case, it's the chromosome column. And then you specify the data type by specifying the function for the data type that you want to use. So in this case, it's going to be col character. So specifying col types with a call to the cols function. The only column type we're specifying is the chromosome column, and we're specifying that that should be col character. So that's going to force it to be text. Having made the change, we also then need to make sure we re-execute this function, because it won't take effect until we rerun the function code to recompile it. Now we can rerun the lapply. And if we look at genome data 1 now, we will see that even though these are all number 1, we get it as a character column, which means that now we can now run the do call, and it should hopefully work and generate our combined genome data. Indeed, it does. And if I have a look at that data, you can now see we have all the data from all of the chromosomes contained within this. Okay. So hopefully that's given you some pointers and also some ideas of some of the pitfalls and problems that you can have when you do this. As I say, there are undoubtedly other ways that you can do this in R, but the methods that I've shown here have been very successful for me. Okay, that brings us to the end of the webinar. If there are any questions, please feel free to ask those now. I'm happy to stay around for as long as we need for those. But otherwise, thank you very much for coming along. There will be more of these in future. If you have suggestions for future topics we can cover, please let me know, and we'll be very happy to try and accommodate those.